Let me walk you through the speaker of this session. We will be delighted to have our speaker Julia and Dipshikha. They are an intern. Julia is working as a data science intern and also graduate as an undergraduate student as well. We will be having a session about diving deep into algorithms, regression, and classification. One more thing I have to mention is the next session we will be having is diving deep into algorithms, naive Bayes, and SVM. We will be having this session on 2nd March 2022, 11 a.m. EST and 9:30 p.m. IST, the same timings. So don't forget to register for the next session as well. Over to you, Dipshikha.
I'll just share my screen.
Sure.
So, hello everyone. Hello everyone. Thank you for joining in. I am Dipshikha. I am from India, and I am currently in my third year of bachelor's. I'm pursuing my bachelor's in artificial intelligence. So, welcome to today's session. Today is the session 2 of our machine learning study group series, diving deep into algorithms, under which we'll be covering regression and classification. The next slide, Sneha. A small recap of what we did in the first session. So in the first session, we covered various topics such as basics of machine learning, the difference between machine learning, deep learning, AI, data science, types of machine learning, supervised, unsupervised, and reinforcement learning, the information about any implementation, the bias variance trade-off, overfitting and underfitting, and other polls. Whatever was covered in the session 1. So in case you've missed session 1, please check the recording in the chat and do ask your questions in the Q&A section. Now we dive deeper into supervised learning in this session. So before that, let's talk about data and what kind of data exists. The data mainly exists in two types, which is descriptive and numerical. Descriptive data is basically, it describes the characteristics of the data set into words like high, low, or good or bad. The second type of data is numerical. Numerical is basically data that exists in the form of numbers and not any language or descriptive form. So again, numerical data can be divided into two, discrete and continuous. So discrete data is basically data in whole numbers. For example, the number of students. So the number of students should obviously be whole numbers. We can't have like, let's say 12 and a half students. So the number of students and the number of units of a property or any clothing apparel sold. The second type of numerical data is continuous data, the data that exists in a continuous range. For example, the height of a person can exist in decimals. So like it isn't only limited to whole numbers. So it can exist over a range of numbers. Similarly, the temperature of a day or interest rates. To the next slide, Sneha. So regression. Regression is a process of finding the correlations between our dependent and independent variables. So it basically helps in predicting continuous variables such as market trends and the prediction of house prices. So let me take an example. We need to predict the weather of a given day. So in this case, our independent variables will be possible cloudiness on that particular day, how sunny it is, what is the humidity, which season it is. So all these parameters act as our independent variables. And the dependent variable will be the temperature. So the output to this example will be a continuous numerical value that we aim to obtain through regression. So in slide 23, you can see in this example, so there's a clip art that indicates all the independent variables, that is sunny, cloudy, or rainy. And regression is what the temperature is going to be tomorrow. So we can use all the independent variables to predict out our dependent variable, that is the temperature, which in this case is 84 degrees Fahrenheit. In short, this example is basically the model is trained on past data, and once the training is completed, it can easily predict the weather. So what is, can you go back? Yeah, thank you. So in simpler words, regression is basically fitting a function from any selected family of functions to a sampled data under some error function, and is one of the most basic tools in the area of machine learning for prediction of continuous numerical data, that is data that exists over a range of values. Can you go to the next slide? Yeah, so in this example, we can see we have strawberries, and the strawberries differ by their size, their other characteristics that exist as their independent variables. And our dependent variable will be the prediction of how much size they are. So the first strawberry that goes in is predicted to be 2 centimeters. The second strawberry, which is mediocre in size, is predicted to be 5 centimeters. And the third strawberry, that is comparatively larger in size, is predicted to be 8 centimeters. Now to other applications, what problems can be solved using regression? So I'll be discussing a couple of examples here. The first example is house price prediction. So let's consider that we have a data set that contains price per square foot, amenities, location, number of rooms, and we need to predict the price of the given house with specifications like suppose I need a house with 2 rooms on 5th floor and stuff like that. So we need to predict the price of the house given that there are other specifications. And we need regression to predict the price of the houses. So houses at different location, let's say house at 13th floor won't be the same as a house in 2nd floor. The second example is time series data. So time is an important factor for weather predictions, as discussed in the previous example. Weather prediction uses, like it makes all their predictions based on the 24-hour window we have for a day. So again, it's a time series data. The third example is a risk analysis of an insurance company. So linear regression techniques can be used to analyze risk. For example, an insurance company might have like limited resources to investigate homeowners' insurance claims that they make based on any damage that they have faced. So with linear regression or with the application of regression, the company's team can build a model for training and estimating their claim costs. And this could help the company to take major business decisions to like regarding what risks to take. The fourth example is predicting and evaluating customer trends. So let's say in a mall, we have like a few items and the trends change with respect to time. So at one time, let me take an example. At one time, the happy or sad octopus plushie was very trending, and the other time slime was trending. So the prices of these products change with time, and regression can be used to predict the trend of the sales with respect to the number of units sold and the prices at which each unit is sold. Now let's talk about linear regression. So far we have covered what regression is and application problems that can be solved using regression. Now we're gonna go over a particular algorithm that helps us solve these application problems. Linear regression is a common machine learning technique that predicts a real valued output using a weighted linear combination of one or more inputs. Let me repeat that. Linear regression is a common machine learning technique that predicts a real valued output using a weighted combination of one or more inputs. Like it's a combination of one or more inputs that predicts a real valued output. Let me break this sentence down into simpler forms. So let's take an example of the example of the graph shown on the slide. The x the x-axis of the graph would, let me refer back to the example of predicting house prices. So the x-axis of the graph would depict the independent variables, that is, let's consider the area of the house, and the y axis would depict the dependent variables, that is the price that we need to predict. So we need an ML model to find our price, and based on the data points that are plotted. In this scenario, we need a straight line that will help us predict the further prices according to the given area. So in this scenario, it becomes a straight line. Now a straight line is modeled by the formula y is equal to mx plus c. So in simple linear regression, we use the traditional slope intercept formula, where a and b are coefficients and intercepts. X is the predictor and y is the predicted value. So x in this case is the area of the house, y is the price of the house that we need to predict, and b is the coefficient of the coefficient of the input variable, and a is the intercept. Let me tell you what a and b are. B is how much our input value will weigh and how important it is. So it's just a coefficient that adds weight to x. And a is the intercept on the y-axis. So a is basically, so no house can have a value, can have a price that is 0. So the line of regression is bound to start from an intercept on the y-axis, which is depicted by A. So finally, X is our input data and Y is our prediction. Now we can see a line of regression here. Let me tell you what line of regression is. So the linear line showing the relationship between the dependent and the independent variables is called a regression line. So a regression line can represent a positive linear relationship with a positive slope and a negative linear relationship with a negative slope, with a downward slope, basically. So can you go to the next slide, Sneha? Yes, so here we can see that our line, the function, is fitting according to the data points position. So what our main objective here is, while working with linear regression, our main goal is to basically fit the line so that our error is minimized. And error is basically the error between the predicted values and the actual values. So the best fit line will have the least error. So in this GIF, we can see that with each iterations of our ML model, the line gradually fits according to the data point while minimizing the error. Can you go to the next slide? Yeah. So in this graph, we can see the red dots are our actual data points, and the line is the predicted value. And the blue lines, which we can see, the blue thin lines are the error. So by fitting the line, what I mean is by reducing the error. So to do this, we use, for linear regression, we use root mean square error cost function, which is basically the average of squared error occurring between the predicted values and the actual values. So we need to average the errors so that the line that is fit is has an equal separation from all the data points, and like the overall sum of the error values is minimized as much as possible. Can you go to the next slide? So the RMSC, which stands for root mean square error, basically measures how much our average model predictions vary from our correct value. So the higher value of RMSC would mean our model is performing bad, which means that the lower our RMSC is, the better our model performance is. So let's take an example here. We have X, Y, and Y pred. So X is our input values, Y is our actual values, and Y pred is our predicted values. Now, RMSC is basically finding the average of the root, finding the root of the average of the errors, squared errors. So error is basically the difference between Y pred and Y. So we sum all the errors, that is 2 minus 0.2, 4 minus 3.8, 5 minus 5. So we sum all of this, and the summation of the squared errors is 3.28. Now the mean of these squared errors. So we find the mean of these squared errors, which is 1.0993, and the root of the mean, because ultimately we have to find the root. So the root of the mean is 1.0456. So this is our final error that we have achieved, final value of the error. Now, how do we know that the value that we have obtained is good or bad? So for this, let me give you 2 examples. Let's say in an example we are trying to find the renting price of an apartment. So the renting price lies typically between $500 to $1,000. So an RMSE value of $15 could be a very low RMS error and the best fit line to satisfy the needs of the person who's renting the apartment. So an RMS value of $15 would be ideal and the best fit, because it is the error value is lower considering the range. In the second scenario, let's say the same person has gone to a restaurant. Let's say the same person has gone to a restaurant, and so the bill price is ranging between $10 to $25. Now the RMSE value of $15 could be very bad because it's high compared to the range, and the line of best fit would not probably like satisfy whatever the person needs. So the interpretation of these scores is basically application related. So unless and until the regression scores, the RMSE scores are from the same application, 2 applications will have their own interpretations of the RMSE score, how good or how bad they are. So are there any questions as of now?
I guess Dipshikha, all are answered by Sneha.
Okay, all right. That's all from my side. So Julia will take over from here. Yeah, okay. So RMSE, sorry, just one slide. Yeah. So RMSE, the formula is basically root of the mean square of the errors. So y1 cap minus yi square is the square between the errors, and by n stands for the mean, and the root is the root over of the whole formula. That's it from my side.
Thank you so much, Dipshikha, for the amazing content covered. So now that we actually know how to predict continuous values, as Dipshikha presented, we're now going to move on to predict classifications. For classification, now we move on to predict discrete values. As we said in like the very beginning, we had like an example, I don't know if you guys remember, of the weather, that we were trying to predict what the temperature of the weather was. Now, when we move on to classification, I can say, for example, that, I don't know, like a weather that is like with temperature higher than 20 degrees Celsius, for me, is a good weather. And a temperature that is like lower than 20 degrees Celsius, for me, it's a bad weather. So now basically with the temperature, I'm not trying to predict the value of the temperature itself, but I'm actually trying to predict if it's in the class of a good weather or a bad weather. So here is where classification in machine learning comes from. So as we said, it refers to a predictive modeling problem where a class label is predicted, for example, of input data. And it recognizes a specific entity within the data set and attempts to conclude how they should be labeled or defined. Another very used example is like when you're trying, like you have a picture and you're trying to predict if it's a dog or a cat. You, for example, like the model in this case, it will look at the ears or the tail, and from that will try to predict if the input data of the picture, for example, will be a dog or a cat. So this is in like general what a classification machine learning model would be. So standard classification algorithms are actually linear classifiers, support vector machines that don't think about it too much right now. We're gonna have other sessions that they're all gonna be covered. SVMs, for example, are covered next session, so do come to next Wednesday if you wanna learn about that. Also decision trees, k-nearest neighbor, which is also a very famous classification algorithm, and random forest. So as I said, like the example before, now we have like input pictures of cats or dogs. And for example, if I have trained the model and my model now, my machine learning model knows how to predict if a picture is a cat or a dog. Now to this model, and don't think about the steps too much right now. This is actually a neural network, which we're gonna cover in the series at the very end actually of the series. So like, don't think about the machine learning model just yet. But just think that we have like trained it and it's now capable of classifying a cat or a dog. So in this case, we would want that if I input a picture of a cat, my model will be able to predict an output as a cat, as you can see in the GIF in the slides. Next slide, please. There is hundreds of applications of classification models in machine learning. Some of the most famous ones are, for example, sentiment analysis. It's one that it's used a lot to predict if, like, for example, I don't know, like a tweet, it's representing positive emotion or negative emotion, neutral emotion. This is also trying to, like, for example, predict pictures of people and like look at the smile or like facial expressions, that you can be able to predict the sentiment that they are feeling at the moment. Also, maybe like the most common example that's always given is like spam email classification. You know that we have this every day in our lives, and it's also a classification machine learning model that is trying to basically predict if an email that you receive in your inbox is a spam or not. And if the model thinks it's spam, it's gonna put it directly in spam and not show it to you. And the other way, if it's not, it's going to put it in like your normal inbox. And we have this, of course, every day in our life. Another very like used algorithm is the document classification. And there are algorithms to predict if, for example, a document is talking about politics, or it's like a letter, or like what different kind of like topic it's covered in this document. And this is also a very used classification machine learning model. Okay, so now like trying to like dive a bit deeper on how this is done. Now we talked about linear regression. Now we're going to talk about logistic regression. And we can think of logistic regression as a linear regression, but now we're not trying to predict the value itself, but we're trying to predict the probability, the likelihood that these independent variables will have of being in a certain class. For example, being a dog or a cat. And how we do this, the dependent variable, of course, are categorical, because it's going to be either a cat or a dog, or a spam or no spam. And they have binary output. For example, we can say that if the picture is a cat, the probability is going to be 1. We give it 1, and for dog, we're going to give it 0. And of course, the binary outputs can be like true or false, yes and no, and always binary. And of course, it's used to solve binary classification. We talked about spams. We talked about the sentimental analysis, for example. We talked about the weather, if it's a good weather or bad weather, the spam identification, of course, and a lot of other examples. now here is where like we really like see the difference between linear regression, because we don't use line anymore, but we use this S-shaped logistic function, which is called the sigmoid function, which is very important when you talk about logistic regression. And it predicts two maximum values, 0 or 1. So the way it does it, as you can see in the picture, we have on the x-axis, we're going to have the independent variables. And on the y-axis is going to be the probability that these dependent variables, the input, the data that we put to the machine learning based on this independent variables, what likelihood it will have to be either of class 1 or class 2. So imagine for this picture, for example, we put at 1 that this picture is a dog, and at 0 that the picture is a cat. And depending on the dependent variables on the x-axis, we then project on the sigmoid function, and basically from the sigmoid function, looking at the y-axis, we can see actually the probability that it says if the probability is, I don't know, 0.7, it means that it has a probability of 0.7 to be a dog if you said dog of 1. And how we do this is by setting a threshold value. In this case, as you see in the picture, we have a threshold value of 0.5, meaning that any probability that is higher than 0.5 is going to go to the 1 class, which, as we said, is going to be the dog. And for any probability that is lower than 0.5, is going to be to the other class, which if we set 0 to cat, it's going to be cat. Again, on the sigmoid function, like if you think about logistic regression separate from linear regression, you can think that you wouldn't be able to use a normal line, because now we're talking about classes. We're talking about 0 and 1, so like one class or the other. So having a linear, it will mean that we have also values that are less than 0 or greater than 1. And that's why we cannot just use a line. And instead, we use this sigmoid function, which basically, as I said also in the slide, is that logistic regression tends to limit the activation function, the sigmoid function that we were talking, between 0 and 1, in order to be able to predict which class it fits. And of course, as you can see, we have the function for the sigmoid function that maps any real values into a value between 0 and 1, as we said. And we also going to have more presentation and more examples in the slides. For example, here we also have a classification model, and as you see, you have a sigmoid model, and every iteration, you can think of B0 and B1 as being parameters of this sigmoid function. And every iteration, they change, they iterate to find the best sigmoid function in order to be able to best predict if, based on these dependent variables, what probability it's going to have. And based on our threshold that we have set, we've previously set, we're going to see if it's a dog or a cat, for example, or spam or no spam. And also like this, always by putting, for example, a dog as 1 and a cat as 0, or a spam as 1 and no spam as 0. Here is like the decision boundary, whatever, like exactly what we were like talking before. If we have this, I don't know, these two classes, like now let's talk about good weather and bad weather. And you have on the x-axis your dependent variables, and you set a threshold. Here in the picture is 0.5, but it depends on the threshold that you put. And if the x values, the input data, projected on the sigmoid function, it's going to look on the y-axis. You're going to look at the probability that function, data belongs to a class or another. So let's say from the x-axis, I am projecting to the sigmoid function, I get a value of 0.4, which is lower than my threshold of 0.5. I know that it's going to belong to class 0. That, for example, if class 0 was good weather, then this is going to be good weather. And but on the other side, if my sigmoid function projects to a value, a probability greater than 0.5, which is my set threshold, then I'm going to say that this data, this input, belongs to class 1, which, for example, would be like bad weather. So this is a bit more how classification works in machine learning. So how do we evaluate if we have made the classification correct? What is the evaluation metric for classification in machine learning? In this case, we actually use accuracy, which is the fraction of prediction that the model got correct. And of course, it can be represented as percentage as well. And it's going to be accuracy, the number of correct predictions over the total number of predictions. So they say, let's say that you have, for example, the model makes 10 predictions of the input being a cat, but actually the number of correct predictions is 5. In this case, your accuracy is going to be 0.5 or 50%. And based on like what problem you're working on in machine learning and what you want to achieve, you also like will look at like what kind of accuracy for you is like, it's a good enough accuracy or not. So this is, as we said, the main examples that we've been referring the whole time, which is regression. We try to predict the continuous value. What is the temperature going to be tomorrow? But when it comes to classification, which we're trying actually to predict if it's a cold or hot weather, or as I said, depending on like what you say is a good or bad weather. So you're trying to predict classes rather than the actual value. Okay, so there's also, okay, because I'm looking at the Q&A, but the question is being answered, so I'll move on. So here you have like 2 examples, and we have talked about regression and classification. So if you can write in the chat, what do you think the first one is, classification or regression, and what the second refers to? No need for a poll here, but just really quick, what the first one, is it classification or regression? Yeah, I see a lot of right answers in the chat, yeah, which makes me very happy. The first one indeed is classification. We're trying to predict, as you say, to divide the blue from the green dots, data points that we have. Whereas the second one, we're actually trying to predict the actual continuous value. And I think most of you did a very good job. So now we're going to start a very quick poll to see how you guys understand the difference between regression and classification. And if you guys can help me with the poll to start the poll, but basically we're going to give you guys some examples and you're going to say if it's a regression or classification. If it is possible to start the poll right now. Okay, here you go. Try to give your answers. I'm going to give you guys a few minutes for this one. Just a few more seconds for everyone to give their answer. I think now it might be a good time to stop the polls and see the answers. So now we can also move at the next slide. Okay, I cannot see the answers of the polls anymore. Okay, here we go. There are some questions that a lot of people have done really, really well, which makes us very proud for the session we just gave. But yeah, for the first one, if this can be divided into linear and non-linear, as we said at the beginning, that's a regression kind of problem. When it comes to logistic regression and decision trees, we're also talking about classification. As we said, the example for classification that we gave was logistic regression, when linear regression was the one for regression. Okay, this can be divided into binary and multi-class, which is, it belongs to classification, and most of you guys got that right. Measured using accuracy is classification, and makes us very happy that a lot of people have answered correctly. And as we said, to evaluate our classification model, we look at accuracy. We look at like the number of good predictions over the number of total predictions. Whereas when it comes to RMSC, that's the case of regression, and also most people have answered correctly. Predicting continuous value, as we said and been emphasizing during the session, it belongs to regression, whereas predicting a discrete value belongs to classification. As we said, if it's a hot or cold weather, whereas for regression, we predict the temperature, the continuous value. And linear regression, as we said, belongs to regression rather than classification, and 97% of you guys got that right. Yeah, these were the answers. We're also waiting now for more questions. If there are, please do post them in the Q&A. And Sneha has also prepared some very interesting demo for you guys, which I'm going to move on after the questions.
Dipshikha, I think there's an RMSC question for you in the chat. If you could take that up, please.
Sure, let me just have a look at the question.
Also, a big shout out to panelists that have been answering the questions all of this time.
In the above example, how do you determine RMSC value of $15 is poor? So RMSC value of $15 is poor in the case of when the person goes to the restaurant and the bill value ranges from $10 to $25. So here the the value lies between the range, and it's more than $10, which is bad. So the higher the RMSC error is, the bad, like the worse our model performs. So we need a lower RMSC value to make our model perform really well. So an RMSC value of, let's say, $2 or maybe like $5 also would have been a good RMSC value in the case of $10 to $25, but not $15. $15 would be unsatisfactory. Has that answered your question, Rupert? Has that answered your question? Any more questions, please ask them through the Q&A section.
There's also a question from Melody, which I think just got answered once now. Please do post your questions in the Q&A box if you have.
Hi everyone. If you have any questions regarding the polls also, you can ask Dipshikha and Julia. They are very happy to answer. We wait for another minute, I guess. Okay, we have one question. Okay, she's saying thank you. That's great.
Please also, if you think about a question later today, like feel free to post it on the Slack channel. And I'm sure a lot of people will be very willing to help you. Also feel free to reach out and to us at any time as well.
Yeah, sure. I guess everyone, let us thank our panelists, and even let's thank our chat moderators as well, who were answering during all the when panelists were speaking. So yeah, thank you everyone for joining. Please join our Slack channel if you have any questions. For upcoming session also, you can join our ML study group channel and you can connect with the speakers as well. Okay, we are going to have the code walkthrough. Sorry, I'm sorry for that. I forgot when I mentioned in the starting. Yeah, you can go.
Yeah, that's okay. I think it happens to the best of us. So thank you everyone for all your wonderful questions. And if you have any more, please feel free to ask us in the chat. For now, I'll be moving on to the code. So you guys can get an example of how exactly regression and classification works in Python.
Sneha, just sorry to
Yeah.
interrupt. People are asking for just a 2-minute break before we start the coding thing.
Oh, sure, no problem.
Yeah. You can everyone can just go grab a bite or something. We will resume in exactly 2 minutes.
Okay, great. I hope it's okay for us to start right now. Does anyone want a little bit more time? You can feel free to put it in the chat box if you do.
Sneha, you're on mute.
Yeah, so I'll share my screen and let's get coding. So if you had taken a look at the link I put in the chat box, as well as many other moderators put, it had the link to a drive where you'd have access to these Collab notebooks. So if you haven't already checked that out, please do. And once you open the notebook, please first make a copy of it. So you can go to the file section here, and then you can go to save a copy in Drive. So when you do that, there'll be a copy that's created of the same exact data set for you in the Drive. So this will take a minute maybe. Yeah. So you can see that this was regression example, and now you have copy of regression example. So you can just change it to whatever name you want. This way you can make your own edits to this data, this particular Collab notebook, and you can run all the cells as per your wish and try and test different things, maybe add more comments as in how you wish. So this is your own copy and you can make whatever changes you want to it. So we recommend you make a copy of both these Collab notebooks before we get started. All right. So first, let's get coding on linear regression. So we learned linear regression is a machine learning model where what we do is we have a set of data points, and we basically want our ML model to be a line that best fits these data points. So for any machine learning model, we need data. So for that, we use different data sets. And today for regression, we'll be using this data set known as the salary data set that I've taken from Kaggle. So in our data set, we have two columns. So if you remember from Dipshikha's explanation, this is the dependent column or the outcome that we want to predict. And this is the independent column or the column that is a feature that basically helps you to predict the salary. So this is what we're going to do. We have these two columns and we're basically going to use this column to predict this column. And this will be modeled as linear regression. So we have salary and year of experience as dependent and independent variable respectively. Now, before we start coding, when it comes to machine learning model or any particular Python programming, we always use something known as libraries. So let me just briefly explain what a library is. So when you think of the word library, I'm sure most of you would have thought of this, of the place where we have so many books. Yes, you can think of Python libraries in that manner as well. So when you go to a library, you have many different books of many different genres. Some may be fictional, some may be non-fictional, and things like that. Similarly, in Python, when we have a library, we have many functions under that library. And these functions basically help us perform a particular task. So I will take you step by step through all the libraries that we will be using today for a regression as well as classification example. So first we have the most important library for data science, that is the pandas library. So how does this pandas library help us? So this library has some functions that help us with basic data analysis and manipulation. So what can we do with this? Whatever data set that we have, we can read our data set. And suppose we want to make some changes to our data set, like we want to add a new value, we want to remove some value, we want to add a new column, remove a column, and things like that. To help our machine learning model do better, we can do all of that using pandas. Next is Seaborn. So we will be using Seaborn as our data visualization library. Now, I've written here that it's based on Matplotlib. So Matplotlib is another data visualization library, but for the scope of this session, we will be using Seaborn. So a data visualization library is one that helps you plot charts and graphs and other things that can help you actually see your data. So when you see your data, you understand more about it and you make better predictions. You can see what model exactly you have to fit into it when you look at the data. So it's always better to visualize the data. Then we have scikit-learn. This is the most important library when it comes to machine learning. It's a free machine learning library and has a variety of algorithms. It has classification, it has regression, and so many other algorithms that we will be discussing in the forthcoming sessions are all present in scikit-learn. Then we have NumPy. So NumPy is basically a mathematical library that's used in Python. And this has a lot of support for, let's say, arrays, matrices, and there are a lot of mathematical functions that are present and that could help us with manipulating our data, changing it into arrays and matrices and things like that. So examples of these will be shown in this as well as the next notebook. So that is about the libraries. Now, whenever we approach a machine learning problem, we have a certain few steps that we need to follow. So I will be going step by step in that regard. So the first and the most important thing that you need to do is import the libraries. You need to import.
I'm sorry. Just mention once again how to create a copy. Everyone, you can. She's beginning the coding part now. She'll just demonstrate it once again so that you can all create copies of this Kaggle, this Collab notebook. She'll show it to you once more how to create a copy.
Yeah, sure. So you have this notebook open. So go to File. And in File, there is this option called Save a Copy in Drive. So you can simply click on that. And it may take a little bit of time for it to load the copy. So yeah. So now you can see that this was regression example. And you know it's a copy because it's mentioned copy of regression example. And you can change it to whatever other name you want. So you can call it whatever else you want. And why we're asking you to make a copy is that this can be your very own version of the same notebook. So you can make all your edits, you can add extra comments, you can try out new commands, and you can basically explore as much as you want with this notebook. So that's why we're asking you to make a copy. So if anyone still has a doubt, please let me know.
Yes, Neha, I guess they have some doubts.
Maybe I'll get to the questions in a bit. I just meant like doubts about creating a copy. You can just put it in the chat or in the Q&A box. Yeah, Hema, Mansi, you can feel free to stop me anytime if there is such an important doubt. So
No, I guess they might need some time, like a minute or so that they can do this task.
Yeah, sure. So I'll just wait for a minute.
So Stacy's asking the link just gets to Collab, but not sure how to get that specific notebook.
Sorry, Stacy, which link is that?
I guess the link that has been sent by Eileen in the drive. Okay, she has asked.
The drive has a folder called code files and datasets. In that code files and datasets, you have a folder session 2, and there you have the regression example notebook.
Sorry, Stacy, you're actually using the wrong link. So the Collab research link that you've put up is actually the link to open any Collab notebook. But in the chat, I guess if any of the moderators could, I think Elaine has put up some link that has the link to the drive. So this is how the drive links looks like, and you can click on that and you will be directed to some folders in this manner. So this link is already present in the chat. So when you click on that, you'll be directed to this drive. You can simply click on code and files and go to session 2. Sorry about that. Yeah, so you can open these two notebooks, regression example, classification example. And in a manner that I just mentioned, you can create a copy of these two. So I hope that was okay.
Yeah, I guess nothing is regarding. I hope everyone is able to make
sure.
a
So
copy.
if any of you are facing any issues, please do put it in the question answer box or in the chat, and definitely one of us will reach out to help you. So for now, I will be moving on. All right. So until here, what we learned was basically about the data set that we'll be using for regression, as well as the libraries, what a library is, and what are the different libraries that we will be using for this session. So now I'll be going step by step on how do we exactly approach a machine learning problem. So first and the foremost thing is you must import the libraries, because these libraries have the functions that help you do certain things. So the first thing you need to do is import libraries. So like I mentioned, we have pandas. So we say import pandas as PD. Now, why do we say as PD or as SNS? Because this PD is an alias name. So what do I mean by that? if you just say import pandas, everywhere that you're using pandas, you'll have to say pandas dot, and it might get a little bit difficult for you to type that out. So instead, if you say PD, that's just a shorter version. So it's easier for you to type it out. So now we're importing pandas here. Then we're importing cbot that was used to visualize our data. Then from sklearn, we have a sub-module known as linear model. And from this linear model, we're importing linear regression. Then again in sklearn, we have something known as model selection, where we're importing train test split. So when we come to this part, I will explain exactly why we're importing this and what this is used for. Then, so if you remember from what Dipshikha mentioned in the session, when we're doing linear regression, one of the most common methods to see what your score or how well your model is performing is to use the root mean square error score or the RMSC score. So for that, from sklearn and the submodule metrics, we import mean squared error. Then again, why have I imported NumPy and what am I going to use it for? I will come to that when we're using it. Then we have this library to remove warnings. So sometimes when you import large data sets, you may get certain warnings from Collab. So if you don't want to see those warnings, you can just add these 2 lines of code. So you can always press Shift Enter or Control Enter to run any cell in a Collab notebook. All right. Now that we've imported our libraries, let's get to the data. So data here. Now here, we've already given you the link to the drive that has the data. So you do not have to change this link or anything else here. So this URL basically has the viewable link for our data set. We're performing some sort of transformation on that so that we are able to read it using pandas. So we have this df variable and using pandas and read CSV. Read CSV basically helps us read a CSV file. Now, most of our data is always stored as a CSV file or a comma separated value file. That's the most common format of files that we use in data science. So we use this df and then we read CSV from this URL. And then we use this command called df.head. Now df.head will basically display the first 5 elements that are present in that particular data set. So that's it. It will display the first 5 elements that are present. So from here on, for the next couple of cells, I will be talking about certain pandas functions that help you view your data. So first we had df.head that basically helps you. Okay, so first we had read CSV that helps you read a CSV file. Then we had head that helps you display the first 5 values. Now we have info. What does this info do? Info basically basically shows you how many columns are there. So for this data set, we just have 2 columns, years of experience as well as salary. Then it shows you the non-null count. That means how many, there are no missing values. So null values are missing values in the data. So for our data set currently, we don't have any values that are missing. So that's why we have 30 non-null values here and 30 non-null values here as well. Then the data type of these values are float. So float is a data type, and the data type of both these columns, the values that are there are of the float data type. Next, we do something known as tail. So head was displaying the first 5, top 5 values, and that means tail will display the bottom 5 values that are present in this data set. Now, let's say you want to know some statistics about this data. In each column, how many values are there, what is the mean, median, standard deviation, and all that. So you don't have to use separate commands for each of this. All you have to simply do is just say df.describe. So df was where your data was stored, as we can see here. And when you say describe basically gives you all the necessary statistical data that you need. So you have the count or the number of values that are there, the mean, standard deviation, minimum. These are something known as quartiles. So I will not be explaining that here. You can definitely feel free to read about them. They're a very interesting topic. And then this is the maximum value that is present in each of these columns. So you get a lot of statistical data with just one simple command. Now you want to analyze the shape of your data set. So what do? You just say df.shape. So you get the number of rows here and the number of columns here. So you can see the number of columns are just 2, years of experience as well as salary. And the number of rows or the number of values, we call them as data points, are 30. Now we run this extra command known as df.isNull.sum. What does this isNull.sum do? Again, it is similar to what we had here. So here, when we put df.info, we got basically the name of the column, how many values are there, how many of these values are not null, as well as the data type. But if we just give this df.isNull.sum, we simply get the number, how many null values are there, how many null values are there. So you can see years of experience is giving 0. Salary is also giving 0. That means that there are 0 null values in both these columns. So usually when we have null values, we do certain methodologies and we try to fill in those null values. Again, that is beyond the scope of this session. So if you're interested, you can definitely read up more about it. And then finally, I'm just printing the columns just for everyone to get understand what are the columns present once again. This will just display the columns that are there, the names of the columns. So you have years of experience as well as salary. So far, we have understood what libraries are. We've understood the different types of libraries that we will be using for this session. And the very first step was to import all these libraries along with their alias name so that you don't have to type the entire name. You can just type the alias, which is smaller. And then we started with some data pre-processing, and we basically took in our data, we read it, and we looked at different methods of looking at it. So we read the first 5, we read the last 5, we got some information about it. We printed out how many null values are there, how many non-null values are there. We also printed out the shape of this data set. That is, we have 30 and 2. And also we just, for us to be sure of what the columns are, we just printed out the columns. So we have years of experience as well as salary. So any questions, any doubts so far?
Everyone can tell us in the chat if they have followed till now.
Okay, so there's this one doubt in the question. Yeah, so this, okay. Okay, so this is just this line is simply a formatting line that helps you to read the CSV file that's present in that location. And this is the URL. So what I did was I took this data set and uploaded it to the Google Drive. So if you actually click on that link that was there in the chat and you go to the code files plus data set, both the data sets, that is the salary data set as well as the data set for the next session, have been uploaded there. So I have just taken the link for that data set as a URL here. And then I've performed just this one basic transformation on that. And then, And then using that, I was able to read the CSV file, which was present in that location. So there were 2 questions based on that. So I hope that was okay. Okay, so this URL command can be used to access Kaggle websites. However, the thing is, you may have to import certain other libraries. And sometimes when you just go to a Kaggle website, rather than reading the CSV file, it could start reading the HTML tags there. So that I've tried that once and that's how it worked for me. That's why I went to the process of uploading it onto Google Drive and taking that link. So if you have any, or if you do come across any commands where you can directly use that link and actually get the proper CSV file, please do let us know in the Slack channels. Thank you for your question. So I'll be moving on. All right. So far we imported libraries as well as we took some time to understand our data. Next, let's spend some more time on understanding data. So let's visualize it, plot it out. Of course, picture is worth 1,000 words. So let's plot it out. Now, as you remember, we used SNS as the alias name for Seaborn. Seaborn is the plotting library. So we've taken SNS here and we've done something known as pair plot. So it's called pair plot. So as the name suggests, an SNS pair plot is one that helps you look at the relationship between 2 variables. So here are 2 columns, that was years of experience and salary. And we want to visualize how does our data exactly look. So given the years of experience, what does the salary look like? So for lower years of experience, the salary is quite low. And as the years of experience increase, we can see that there is a sort of an increase in the values of the salary. So this is what the SNS pair plot helps us do. So X variable is what we want to plot in the X-axis, which is our year of experience. Years experience, that's the name of the column. Then Y vars, that we have to give in the variable that we want to put on our Y-axis, which is salary. Then kind. So kind could be either a line plot, a bar plot. There are different kinds. So the best way for you to learn all about Python libraries is actually to go to the documentation. So if you go to the documentation, you will understand each and every word that's present in that. So there are different kinds of plots that you can do. But for our case, in this example, I have taken scatter plot. And data is df. So as you remember, we read the CSV file into df, and that's what we stored it into. So that is the df. And then I've just taken the size of the plot as 5, and so that it's large enough for everyone to view. So that is about pair plot. It helps you visualize the relationships between two different columns. So now that we've visualized our data, let's move on into the machine learning part of things. So far we dealt with the data and the libraries and all of that. Now comes the actual machine learning. So if you remember from our first session, how do we usually deal with data that's given for modeling? We don't use all the training data that's given, and we don't train it on the entire data and test it on the entire data. So that would mean, like, suppose you're preparing for an exam. So you are studying some material. You have no idea what the questions are going to be asked on the test. So you are studying some material, that is the training data. You have no idea what's going to be asked on the test. So that is the testing data. So you'll be studying, learning, training yourself on the training data, and you will be testing your understanding on the testing data. Isn't that what normally happens when it comes to exams? Similarly, a machine learning model works. So it has some data on which it will train and some data on which we test it to see how well it is working. So that is what I mean by splitting the data. Usually we split it into 3 types: training, validation, and testing. But for the sake of both of these notebooks, I've only split it into train and test. So training, validation, and testing. Validation is again, so if I have to go back to that example, training is that you're studying from your notes, your PPTs, your textbooks, and everything. Now, validation is you yourself are forming some certain questions and you yourself are trying to find the answers to that. And testing will be the actual exam. So that is the most ideal way for you to split your data. But for the sake of just these 2 examples, I've split it as train and test. Now, how do we do that? So first, you take an X variable. Now, your X variable will just simply have the independent column, that is the years of experience. So in our case, we just have one independent column. When we come to this notebook, we will have more than one independent column. So I will repeat what is done there as well. So we have this just one independent column. And then we have a dependent column, that is salary or the outcome that you want to predict, and that will be Y. So we split it into X train, X test, Y train, as well as Y test. So we split it into these 4 parts. And we usually, what we do is that we give training a larger half of the data set and testing a smaller half of the data set. So in our case, I've given the test size as 0.3, or just 30% of the data goes for testing, while around 70% of our data set goes for training. So that's what I'm doing here. I'm taking 4 variables: X train, X test, Y train, and Y test. And I'm calling that train test split. So we had imported that here. From sklearn.submodule model selection, we had imported train test split. So I'm simply calling that out here and splitting the data that was present in X and Y into these 4 variables, taking the size of the test as 0.3 and this random state 42. So what does a random state mean? A random state means that every time you start splitting the data, there is one particular value from where it starts. From where it starts to split it into train and test. So that value is preserved. That's why we give a random state. So that's about how you split it. So you split it into X train, you split it into X test, Y train, as well as Y test. Now, this is what your X train looks like. So these are the years of experience. These are the indices given. These are the indices, and these are years of experience. So they have taken random indices and years of experience. So you know that X just simply has the years of experience. So it just takes these indices as well as the years of experience. Now, the problem with the data looking like this is that a machine learning model always requires data of a particular format. So usually when we go to machine learning models, it will require numeric data. And for this numeric data, it cannot be in this type of a format. It requires it in more of an array format. And for that reason, we use NumPy. So we take this xtrain and xtest, and we basically use this np.newAccess function. So np was again the alias name for NumPy. So we take this np.newAccess function so that this type of data, this is how our xtrain previously looked like with the indices as well as the values. And now this is how our xtrain actually looks like. So all of these have been put into arrays, and these arrays is what will be used for our modeling and prediction. So that's why we're using NP over here. And we split it into xtrain, xtest, ytrain, and ytest. Our xtrain was like this, which is not a format acceptable for our machine learning model. Hence, we're using this np.newAccess to basically format it in such a way that it looks like this. And this is more feasible for our machine learning model to train on. So I hope that was understandable so far. Now we're on to the very last step. So we imported the libraries, and then we read our data, then we visualized our data. And now recently we have split our data into training as well as testing set. So the training set is what our model will train on. Testing set is what we will test the model on to see how well it is performing. And then we reformatted our xtrain in such a way that it's feasible, it's in a good format for our machine learning model to train and test on. Okay, so that's what we've done. Now our final step. So we took from sklearn, we'd imported linear regression. So what we do is we create an instance of this model. That is, we just basically store the model, the linear regression model, into this variable. Now what's the next thing we need to do? So as I told before, the first thing we need to do is training. So for training, we use this function known as fit. So we take the model and we fit it on the training, that is xtrain as well as ytrain. So xtrain has the years of experience, ytrain has the salary. So what our model will do is, looking at the xtrain and ytrain values, it will try to understand the relation between these two values. That is the dependent variable is the salary, independent is the years of experience. So when you call model.fit, it will.
I'm sorry to interrupt, Sneha. Can you explain np.newAccess again? There's a question regarding that.
Yeah, sure. Okay, so np.newAccess is basically a function that, so you don't want these indices to be present, right? Now in your xtrain, so we're actually calling np.newAccess on both xtrain as well as xtest. Now when you have xtrain, you have these indices. So our xtrain value has been taken from random places in our entire data set. So it has the indices of the same as well. So we have 0, 4, 16. And these are just series of data. We don't want it as a series of data. We want it as an array. We want that data to be stored in an array-like format. Because if it's not stored in an array-like format, our machine learning model will be confused as to how am I supposed to use this data? It's just series. I don't understand. There is a random 0, a random 4, a random 16. Along with this, are these both features? It won't understand. It will throw you an error. For that, we basically take all the values in the row, and then we call this np.newAccess function. np.newAccess will basically transform this into every, so if you see 1.1 here, 2.2, 5.1 gets stored in this manner. So it's a large array, and each element gets stored in an array of its own in this manner. So large array with subarrays of each element. So when the data is presented to the machine learning model in this format, it will be able to understand and model it as well. So I hope that cleared your doubt.
Sneha, can we wait for a minute before we proceed, so that people can ask any questions or grasp any learning that they are having?
Yeah, sure, no problem.
Yeah.
If some of you or most of you have created copies of this and you want to run it along till whatever code block Sneha has reached, you can just do and check the outputs as well for yourself. And then
sure.
we will in exactly 1 minute. So you can ask your questions in the Q&A section in the meanwhile.
Yes, I'll just pause for a minute so that you guys can feel free to ask your questions and any other doubts you have. I think Stacy put in the chat that the machine learning model was created to use an array. So you need to convert your data to an array, if not already. Yes, that is perfect. So that is why we use the np.newAccess function.
We have some questions, Sneha. Do you want me to read?
Yeah, sure.
Can you repeat what's the random state argument in the train test plate function, please?
Okay,
Do you
I
want to
think
explain?
Mansi answered that. So I'll take the
Okay.
question that's right on top. So when it was put into an array, the years of experience was lost. So that is actually incorrect. Let me reshare my screen so that this confusion is clear. All right. So X train, X train, as I said, is years of experience. X is years of experience, Y is salary. Now, this 1.1, 2.2, 5.1, 2.9, 4.1, these are the years of experience. Now, this is the index. So let me go back here. Right. So can you see 0, 1, 2, 3, 4? That is the index of the value. So when you take a data into an Excel, you'll always have the row number, right? 0, 1, 2, 3, 4. So that is what that is. That is what this 0, 4, 16, 5 are. So Xtrain has taken data at the 0th index, at the 4th index, at the 16th index, at the 5th index, at the 13th index. And then it has basically taken this as the Xtrain. Now, when we want to train our model, we have no use for this index column at all. And this Xtrain is not in a format that is going to be useful to the machine learning model. So what we do in that case is that we use the NP new axis. So it's not the years of experience that's lost. It's the indices that are gone. So when the index is gone, you don't really need the index. How is the index going to be useful? It's not a feature at all. It's neither a dependent variable nor an independent variable. It just keeps count of the data point. So you don't need this indices, and you need the years of experience in a format like this, like an array with a sub-array, so that it is understandable to the machine learning model. So that's why I use np.newAccess, and years of experience is not lost, the index is lost. So I hope that cleared up. That cleared up things for you. All right, I will be moving on. Okay, so thank you all for your wonderful questions. And so what we've done so far is that we've modeled our Xtrain into a format that will be useful for the machine learning model. Then what we do is we use this model variable to basically create an instance of the linear regression model. We are storing the linear regression model that we previously imported. So if you remember this, if you remember this area, sklearn, the submodule linear model, and from there we imported the linear regression function. So this function, this just one function, will absolutely do linear regression for us. So we've imported that and stored that in the model here. Then, like I mentioned, the very first step, when you're preparing for an exam, what's your very first step? To actually study for an exam. So the studying, for the model studying phase is known as training. And we use this function called fit to actually code that out. So when you want to code out the training phase of a model, we use fit, and we pass in Xtrain and Y-train. So Xtrain will have years of experience, Y-train will have the corresponding values of the salary. So when Xtrain and Y-train are given like that, the model looks at the years of experience and then looks at the salary, and then is trying to find out the pattern. So actually, when we look at this, we look at years of experience, we look at salary, we can see that it's linearly increasing in this manner, that as the years of experience increase, the salary is also increasing. So now we need to teach that to the machine learning model. So that is why we use the fit function, that is training. Now we're done with training. Now we have to put the model to test. So what we do, we take this variable called ypred, and we have some X test here. So X test again are some years of experience that the model has never seen before. So the model trained on Xtrain as well as Y-train. So it trained on Xtrain and Y-train. That was like 70% of the data set it trained on. Now this remaining 30% it has never seen before. It has absolutely never seen before. So what we do is to this ypred variable, we again take the model, that is our linear regression, and we predict the value of X test. So X test again is 30% of the data set, 30% of the years of experience that the model has never seen before. So that is what we're passing here. Now, in this manner, we're testing. So like I mentioned, when you're actually studying for an exam, you train on what is given to you, and the testing questions that come to you as a form of a question paper, they're usually quite unseen. Like you've never seen these questions before. These are quite new. They're similar to your material that you studied, but they're not the exact questions that were there in your material. They're quite different. There may be a twist in it and things like that. So similarly, this X test is data that the model has never seen before, and we're testing it on this data. So now we have our Y-pred values. That is, we took some unseen values of what? Of years of experience. And we took these values of years of experience and we're trying to predict the salary. So the model has predicted its salary values based on this. Then we need to find out a score of how well our model is doing. So to find that out, as was previously mentioned, root mean square error is one of the very popular metrics that are used for linear regression. There are several other metrics as well, such as R2, simply mean squared error, and things like that. But you can definitely look that up if you're interested. And for this session, we're using root mean squared error. And root mean squared error, we pass in the Y test values. So this X test, the corresponding actual answers. So you can think of Y test as the answer key for X test. So whatever was the 30% of the data set that the model has never seen, the corresponding actual answers are Y test. Now Y pred is what the model has predicted. And why are we saying squared false? So like I said, there is mean squared error as well as root mean squared error. Both of these are metrics to measure how well your linear regression model is doing. For this session, I wanted to explore root mean square error. So when you set squared to false, you always get a root mean square error value. By default, it's set to true. So if you omit this statement, you will simply get a mean squared error value. So you can definitely try that out after this session as well. And what I'm doing in this last step is I'm simply printing it out. So when I print it out, I get the RMSC score as 6146.92. Now, if you look at the salary that's there, so there are quite large ranges of salary. And the mean salary we have is somewhere around 76,000. So 76,000 is our mean salary. Why? Our root mean square error is 6146. So it is much lesser compared to our actual mean salary. What does this mean? This means that the error is much lesser. Definitely. So this is quite a decent value. That means our model has performed quite well. Definitely there can be ways we can do to improve the score and make it even lower. So that is something you guys can definitely explore. But for now, this score is quite decent and the model has done quite well on this unseen data. So it has passed the test. All right. So that was about our model. We took a linear regression model, we trained it, we tested it, and we got a score. Now, just to visualize like Dipshikha mentioned at the beginning of her session, linear regression is simply fitting a line to your data points. So just for everyone to understand how that line is fit, we use something known as reg plot or regression plot. We are given years of experience, salary, we given our data, and we given fit regression equal to 2. So it makes sure to relate these two variables in the form of regression, and we plot it. So we get years of experience, salary, and the line that best fits it. So that's all about regression and the code required for regression. So since we're running short of time, I will very quickly go through classification. But before that, any of you have any doubts? Okay, so Namita is asking in the chat, why is RMSC so high? So actually, Namita, let me just re-explain RMSC for you. So RMSC is basically a value that is dependent on our outcome. So what was our outcome in this case? Our outcome was the salary. So if you can look at our salary, there are such huge values of the salary, right? They're so huge that the mean salary value, the average value of the entire salary column is 76,000. So when you have the average of the entire salary column as 76,000, your aim with RMSC is to reduce the error, reduce the root mean squared error. You want to reduce the root mean squared error value. So what you want to do is that you want the value to be definitely lesser than this. So the lower it is, the better. But this the range for our salary column is quite high, right? So we can't have very low values as well, but the lower the better. So the fact that we got a value that is much lower than our mean is quite good. So always an RMSE quite depends on the outcome or the actual values that are there in the outcome column or the dependent column. So I hope that answered your question, Namita. All right. I will be moving on to classification. So now for classification, sorry. Is there any range in which the RMSE should fall? So RMSE again always depends. The range for RMSE should be okay. We have the salary column. Now our salary column's minimum value is 3,000 something, and our maximum value is 12,000 something. So this is the range of our salary column. Now, ideally, if our RMSE score goes below this minimum value, that would be quite an excellent model. So our RMSE value was somewhere 6,000. So it was closer to the lower end of our range. So the range of values for which an RMSE should fall under always depends on the range of values for the outcome column. So the outcome column is salary in this case. And 3,000 to 12,000 is the range for
I'm sorry, it's 1,32,000. Yeah.
Yeah, 37,000 and 1 lakh. I'm so sorry about that. So so 37,000 and 1 lakh. That is the range of the salary that's given here. So actually, we got a value that is lower than our minimum value. So that is quite good performance. And range of values will always depend on the range of our outcome column. So that in this case, I'm sorry for reading it wrong. It was 37,000 and 1 lakh. So since our RMSE value was lower than the minimum value, it has actually done quite well, but we always have scopes to make it better by improving certain parameters, hyperparameters and things like that, more of which you can definitely explore on your own. So, Namita, was that okay? I'm again sorry for reading the values wrong. Okay. Okay, so I'll try to quickly go over the Titanic data set. So again, so this Titanic data set basically contains information about the people who were aboard the Titanic ship and whose sinking is one of the most infamous shipwrecks in history. So like I went over some steps over here with respect to importing data, data pre-processing. The exact same steps will be followed for almost all the machine learning algorithms. So again, you start by importing the necessary libraries. So I'll just go over the libraries that are different due to the interest of time. So there we used sklearn, linear model, but linear regression, and here we're using logistic regression. Over there we used sklearn metrics mean squared error, here we're using accuracy score. So these are the only two different things that we'll be doing here. The rest of this plus the visualization, that is the only thing that's different between regression and classification. Everything else will remain the same. So we again have Panda, Seaborn, we have the train test split to split it into train and test sets. And again, we have this to remove warnings. So similarly, we take the data and we read it and we print out the first 5 readings. So if you actually go to the Titanic data set that is there on Kaggle, you will find that for some columns like these, and some others, there will be a lot of categorical values. That is, there will be F, M, Q, C, S, and things like that. Now, like I mentioned before, for our machine learning model to work, all the data must be in a proper format that is feasible for it to work on. So in that case, if we give the machine learning model, let's say like C or F or M and things like that, that is categorical variables, it will not be able to model it properly. So for us to help it model properly, I have converted all of these columns, the values, into numerical values. So once you convert it into numerical values, it becomes easier for the machine to understand what these values actually are. So basically, these are categorical values for these 3 columns, which have been converted to numerical values. And the age and the fair was basically, so the age values were like a proper age, like 22, 33, 44. So what I tried to do was to put them into certain bins. And bins as in I took like 10 to 20 age as number 1, 20 to 30 as number 2, 30 to 40 as again number 3, and things like that. I did a similar thing with fares as well. So this is just an overview of the explanation of what I did with the data set. It's okay if you don't understand it at this stage. We'll be talking more about it in the forthcoming sessions as well. So again, similar to the previous notebook, we have read the first 5. We have imported the information. So now we don't have just 2 columns. Rather, we have this column, survived. Now this is our dependent column. And all of these are our independent columns. So last time we had only 1 independent and 1 dependent column. But here we have this as our dependent column and all of these as our independent columns. And as you can see in this non-null, we again have 891 non-null values. Then we again display the last 5 elements. We display all the statistics that are there in each of these columns using describe. Then we display the shape. So 891 rows, that is 891 data points and 10 columns. Then we do is null.sum. So we have 0 null values in all of these columns. And then again, we just print out the names of all the columns. So that was about, again, it was exactly the same, functions that we did over there. We're doing here as well, just to see and have a look at our data. Next, we move on to data visualization. So for data visualization, again, we're using Seaborn. So last time we used something called a pair plot, but now we'll be using something called a count plot. So we're taking P class and survived. Okay, now P class is basically the class where the class of the cabin. So the class of the cabin was 1, 2, 3. Okay, so that is basically P class. So if you remember the Titanic, the 3rd cabin was the lowest, then was the 2nd, and then was the 1st. So if you see here, 0 survived is 0 or 1, and 0 means that the person did not survive, and 1 means the person survived. So that is what 0 and 1 mean. And so this count plot, what it does is it takes the survived as well as the P class. And for each of the P class, that is each of the cabin numbers. So P class again is a cabin number. So 3 was the bottommost, 2, and then 1. And for each of these cabin numbers, it gives you a range or a count of how many people survived. So you can see that there were quite a few survivors. There were more survivors than the people who didn't survive in P class 1. Why was this? Because P class 1 was right on the top. So the first part that was submerged was right at the bottom of the Titanic, right? So that was what was submerged first. That's why if you see in P class 3, there are more people who didn't survive as compared to the ones who did survive. And P class 1 and 2, so P class 2 had around the same range of people who survived and didn't survive. And P class 1 had more people who survived compared to those who did not survive. So that's about P class. Now we have sex male. So this shows you for male and female. So this is female, this is male and this is female. Oh, sorry, the other way around. This is a female and this is male. So 0 is female and 1 is male. And it shows you the count of the people. Again, it's similar to this. So here also you had 0, 1, 0 indicating the count of the people who survived, who didn't survive, 1 indicating the count of the people who did survive. Similarly, here we have 0 and 1. And if you see in females, we have a higher count of the females who survived in comparison to the males. And for male, we have like a higher count of males who did not survive. And in females, we have a higher count of females who did survive. Now, can you possibly tell me in the chat, why do you think that is? Like, why do you think that, there is this kind of a disparity? Why do you think, like, go back, think about what happened in the Titanic and think about why there are more women who survived compared to the men based on that. Yes, exactly. So Shaw correctly answered that in the chat. So when the lifeboats were sent out for the Titanic, first we had female and children boats that were sent, and then were the males. So that is why there's a larger count of female who survived compared to the males. So I have just basically plotted similar plots for all the different features. So SIB-SP stands for sibling and spouse. So this means that they had no sibling and spouse, 1, 2, 3, 4, 5, 6, 5 and 8. There was no 6 and 7. So again, it shows 0 indicating people who did not survive, 1 indicating people who survived. So SIB-SP means sibling and spouse. Similarly, PARCH means parents and children. So PAR parents, CH children. Again, this means 0 parents and children, 1 parents and children, 2, 3, 4, 5, and 6. So again, 0 indicating the number of people who did not survive, 1 indicating the number of people who did survive. So this was just extensively count plot. Count plot was used to show based on the given features. There are many independent features in this data set. So based on the independent features, how was the dependent feature model? So this is, so in data science, it's always important to think of the domain. So here, when we think back to the Titanic, we understand that when the cabin 3, there were lesser survivors because it was at the very bottom. There were more female survivors because it was the female boats that were sent out first. Okay. And finally, we have something called a heat map. So this is a very common map in data science. What we do is, to this SNS heat map, we pass in df.core. So what does this do? This basically models the correlation between the two given columns that are present in the data set. So you can look at the value. So this means a positive correlation and this means a negative correlation. And you can see, so when the columns are exactly the same, they have complete one positive correlation because they are the exact same. And you can see when they're darker, they mean they have a negative correlation, and any other value could be somewhere in the middle. So this is the scale. And this basically shows you which column to which column has how much correlation. And you can figure out how much correlation is there based on this scale. So that's about heat map. And it's very, very commonly used in data science. So this was the data visualization. Then again, similarly, we do the splitting exactly as how we did there. We do it here. Only difference is that we have more independent columns here. So if you go back here, we simply used years of experience as X because there was only one independent variable, and salary as Y because there was only one dependent variable. So here we're doing the same thing. Survived is the dependent variable. We want to predict if, given these many independent variables, if a person survived or not. But the independent variables are many. So what we do is, instead of so one by one listing out the columns of the independent variables, we simply take the data frame, the entire data frame, and we drop the last column. So if we did not do this, then we'd have to say df, and then we had to open brackets and again say each of these. So p class, sib sp, p arch, sex male, embarked, ages and fair. So we have to go one by one for all of these. But rather than doing that, with one simple command, we can just say df drop, and that particular column that we want to predict, that is the particular dependent column, we dropped it. And similarly, we split it. And this time the test size was taken as 0.2. So 20% for test, 80% for training. And exactly similar to this code. So if you look at these two codes, they will look exactly the same. So again, we create an instance of the logistic regression. We go through our fitting or the training. Then we predict it on unseen data. And over there, we used an RMSC score. But for machine learning, for classification, we usually use accuracy score. Now, in the forthcoming sessions, we'll be talking more about accuracy metrics, and we'll be going into better metrics such as accuracy, precision, confusion matrix, and all of that. But for this session, we've just used the accuracy score, and we've taken it on the Y test and Y pred. So we've taken it on the predicted values on the unseen data, as well as the actual values. And based on that, we are predicting the accuracy. So accuracy is always a percentage. It is basically the number of incorrect values by total number of values into 100. Sorry, the number of correct by total into 100. So I'm just, when I don't do into 100, it will just come as a decimal. So I'm just trying to model it as a percentage. So we get 80% accuracy. So the accuracy with which our machine learning model has predicted the survived or like survival rate of the new passenger, like that is unseen data, was actually 80%. So that is what we've done with accuracy here. So here, the higher the better. And here with RMSC, it was the lower the better. So you can see that there was a similarity here. And the difference we had was just in the data, because we're using two different data sets, and definitely the evaluation metric. So that's all from my side. And any doubts?
Yes, we have on the question Q&A box.
Yeah. Yeah, sure. So I can share that data. So that was, I decided not to show that here because that would become too much to understand, especially for beginners. But if you're interested, definitely drop me a Slack message and I can share that with you. Interpret the heat map conclusion she made for the columns embarked S and embarked C. Embarked S Okay, this means that, okay, so these values, right, what we have already done is we've taken it into numerical data. Now, if we had plotted the heat map on actual values that was not converted into this format, then this heat map has much higher value. But essentially what this means is that they have a negative correlation, as in when one increases, the other decreases. But since we've already formatted the data into this format, that is this format, I don't think you should look too much into that for our example. Normally, people make a heat map on data that is not processed just to figure out the correlation between the different columns. So more the correlation, then if there are two columns that are highly correlated, what happens to the machine learning model is that it becomes very complex. It could be highly positively correlated or highly negatively correlated. Positively means when one increases, the other also increases. Negatively means when one increases, the other decreases. So it could be either of these. And we do not want this exactly because that could increase the complexity of the machine learning model. So usually we try to keep our correlations as little as possible. Of course, ignoring the diagonal because that is exactly the same column. But yeah. Why is it such a dark black square? Yes, that's because they are negatively correlated. So if you see on the scale, the lighter shade meaning they're positively correlated and darker shade meaning they're negatively correlated. So I hope that answered your question, Shaw. Okay, so that's all from my end. And
last question.
Yeah, I just saw that. So Shaw is asking again, would you have dropped these two columns to create the ML model? Now, so Shaw, like I mentioned, this might be a little confusing for you to understand, but what I have done is that I have basically taken the data and modeled it into its numeric format. That is why you can see a lot of correlation in this case, because it's not in the original format that it was there. In the original format, it was modeled as a categorical data that was S or Q or, sorry, what was that? S or Q or C. But what I have done is that I've modeled it into numerical data. So now that when it's in this numerical form, it's showing this much correlation. But it is still very important when it comes to predicting the machine learning model. And in this case, it will not increase any complexity because these data have already been converted into their numerical form. And because they've been converted into the numerical form, it will actually help us with making our machine learning model better and making our accuracy better. So yeah. Anything else?
No, I guess there are many appraises for you guys for such wonderful session.
Sorry, Shaw is
Okay.
asking one more. Shaw, do you mean the strain test split? Could you just confirm that? Oh, okay. Yeah, so this was again, this was just, so I've also not looked too much into it. I just took it as, you know, I took this as one of the formatting guidelines. So usually we have many ways to format a URL so that it becomes easier for us to read it. So I just took this as a syntax for basically formatting this URL in such a way that our read CSV is able to read and print out the data set from there. That's all. So if you want, I could look into this a bit more and give you much more detailed explanation in the Slack channel. Is that right? No, the URL first variable was not sufficient because that was the one that was explored, that was given to my own personal drive. So this is basically to make it into a format such that you're basically taking the important part of this URL and then reading the CSV file from there. You do not need this view, USP sharing and all of that. Okay.
You can give shout out to our speakers. You can join our Women Who Code Science and Python communities as well. Shrishti has already shared all the post links and our social media handles as well.
Thank you everyone for joining in, and thank you so much for staying till the very end.
Thanks,
Thank you, Shaw, for your
Shaw.
insightful questions.
Yeah, we really like such an enthusiastic person so that they are asking so many questions. It makes the session more interactive. Thanks, everyone. We can catch you up for the next session that we will be hosting. So you can have all the day events and notifications present on the Slack channel as well. Please try to join it. And you
We
can
have
ask
our,
the questions anytime. Yes, Sneha?
sorry, we have our next session about SVM and naive Bayes, which are two other algorithms in machine learning. So we'll have it again next Wednesday at the same time. So hope to see you all there.